Our speaker today is Andrea Rossi, who's part of INAF since 2013. He has research on optical near-infrared follow-up of gravitational waves and gamma ray bursts, and he studied the Ross galaxies. He's also a night astronomer for the LBT Italian team, meaning he's responsible for the execution of INAF programs at the Large Binocular Telescope. Just let me remind you all that starting from today, since we switch platform, we are doing that on Zoom, kindly provided by the INAF Observatory. The talk will also be available via the YouTube channel of the Observatory later on, because our speaker, of course, agreed to do so. So please, Andrea, the stage is yours.
Thank you, Franco. So first of all, I would like to thank the Observatory for giving me the opportunity to give this talk. I will talk about the hunt for kilonova. And first, I will speak about general kilonova associated with gamma gravitational wave signals and short gamma ray bursts. Then I will use this for a comparison between the short gamma ray burst optical near infrared counterpart and the famous Kilonova AT 2017 GFO, the only spectroscopic kilonova. And I will use this to build constraints on kilonova luminosities. And I will finish with future perspectives for the next rounds of gravitational wave signals and searches of kilonova. So you probably remember the discovery of AT 2017 GFO. On the 17th of August 2017 is what I like to call a 3-in-1 event. We have the gravitational wave signal, short gamma ray burst. You can see here on the left. The green is the area covered by LIGO Virgo, the localization in the sky map. And this in blue here is the localization of the gamma ray burst from Fermi, and his Chang stripe is the localization from the IPN localization system. And this is, and then we have the kilonova. And this is the first spectroscopic kilonova. So in all, we have three some records. This is the first gravitational wave from a binary neutron system detected. This is the first one gravitational wave signal with an electromagnetic counterpart, a gamma ray burst. And it's the first evidence in this way that the short gamma ray burst origin from a merger of two compact objects, in this case, two binary neutron star system. And it's the first spectroscopic kilonova, AT 2017 GFO. Which you can see here in this within this green area. This is the first image of this kilonova. It was found by the 1-meter telescope SWAP, 11 hours after the trigger by LIGO Virgo, and this is the spot which was not visible 20 days before in the LT40 images. So what we have here, we have a kilonova, which is a thermal emission powered by the radioactive decay of heavy elements formed via rapid process capture nucleosynthesis. And the striking features of this kilonova emission are two. We have a blue kilonova, okay, which resembles what we can see in some collapsar supernova days after the explosion, okay? But in this case, in case of a kilonova, disappears very quickly, okay? 2 days after, this is 18th of August, 2 days after, was nothing. This blue component was not visible anymore. And instead, we have a red component with this fading much slower. And you can see this on the left. You have on the left, you have these bands. These are the near infrared bands, which are almost flat. This component is almost flat. Okay, and this drops after 10 days. Instead, the blue component fades very much quickly. And these two components are the striking feature characteristic of a kilonova, which means that there is something that we cannot compare with anything else. Maybe the shape of the spectra resembles a little bit that of collapsar supernova of the first spectrum. So to follow up this, to search and follow up these electromagnetic signals connected to gravitational wave events, we in Italy built a team, the Gravitational Wave Italian team, which we devoted to our time to the follow-up of the search and follow-up of electromagnetic signals. So this is not an easy game, as written in this sketch from given me by Stefano Covino. So what happens? We have the LIGO and Virgo detection of a gravitational wave. Okay, then we have the identification of the gravitational wave, and which also builds a sky map. Okay, localization in the sky. We don't start immediately. Further, we have to wait for the event validation because a lot of signals may be coming from Earth, so it can be noise from Earth or spurious detections. So we can use this time, 15 minutes, 30 minutes, to elaborate better our strategies to decide which with which facilities to go first and to build our scripts. Then after we have the confirmation that this is a real astronomical source, we can start first triggering the larger field of view telescope, like for example we have access in Chile to the DST, or Asiago, for example, the Schmidt telescope. And then when we find a candidate, we can trigger the bigger telescope with smaller field of view, but we can use them to characterize the source also spectroscopically. Here on the left, you can see the sky map of LIGO and Virgo. You can see these lines here as covered by different pointings from VST, the 1 degree field of view VST. This I think is sky map from gravitational waves in 2015. So from the south, instead, we are part of the NGRADE collaboration, which uses ESO facilities. Okay, so VLT and especially in the optical, and is a group of all the European researchers that want to use the ESO facilities for the characterization, in this case, of the candidates found by other means via, for example, by search, for example, also by gravity. There are over both theoretical and observational expertise together. This is very important because within this big team, we can exchange idea. There are expertise coming from different kind of research, from supernova searches, galaxy searches, from radio also, because also we have access to ALMA, to gamma ray burst. And after 17, the biggest search was, most productive search was the follow-up campaign for gravitational wave 1908-14BV, which is a candidate network star black hole. It was localized in this region here, a small localization, but it is at 270 megaparsecs, so it's quite far away. Okay, it's almost factor 7 compared to AT 2017 GFO, which was at 40 megaparsec. So we need to go much deeper, and we did the search within this small area. Well, it's not so small. In 2 ways, we're using old wide field of view telescope like DST, or a smaller telescope like GO2. Atlas, for example, or with the targeted galaxy observation. So we targeted the galaxy, which is smaller field of view, using, for example, OCAI, the galaxies that are within this sky map. And this way we reached to deep limits on what is called the tidal dynamical ejecta of the kilonova, which is the one producing especially the red component, which is a striking feature, characteristic feature of the kilonova, which we could use to 1 sigma. We could put upper limits of 0.1 solar masses to this component, which is already something. Although, unfortunately, nothing. We could find no electromagnetic counterpart. But the only neutron star black hole events which are confirmed, so we'll go very quickly on this, are actually these two, 2115 and 2105 at 300 megaparsec. Unfortunately, there was a non-electromagnetic counterpart found. Also, the search for this was very difficult because in one case, the largest area of the localization for gravitational wave was too large for follow-up, and also the visibility was very bad for large part of this area. And also in the other case, it was basically not visible from ground because it was only daytime. There is reported in this paper from Anand the coverage of 50%, less than 50% of the sky from them. So now I want to go back to the Kilonovae associated to the short gamma ray burst. I talked already of this 17 What happened? What we have? I mentioned that we have a short gamma ray burst and the kilonova. So the kilonova is when we have the merger of two component objects, for example, two neutron stars, and they can merge in forming, for example, a black hole or a neutron star or a neutron star, long-lived neutron star, and that they can collapse in a black hole. This is what is called the tidal dynamical ejecta, emitting the shallow decay near infrared component. Then we can have a disk here close to the center, the accretion disk, which can emit the blue component or red, depends if you have a black hole or if we have a neutron star at the center of the black hole. Then we have also a polar component, which probably is what we see in case of 17 and we have a jet, a relativistic jet, which is what is emitting gamma rays that we see at gamma ray burst. And then when it expands, interact with expands in the interstellar medium, we see as afterglow. And in case of 17, this was detected in X-rays and in radio. So, however, this is a big sketch of what we know now of kilonova. What are all the known or claimed kilonova? We have just one single event with the spectroscopic follow-up, 2016 GFO. It's also the only one observed after a gravitational wave signals. All the others kilonova claim, like 10 of them, are related to short gamma ray burst, not related to gravitational wave signal. And this is the last one we reached. I will talk a little bit later about this. So we have a lot of kilonovae associated to short gamma ray burst. What we can learn from this? We can use this to put constraints on the luminosity of kilonova, but we have to be careful because in short gamma ray burst is this afterglow component coming from the relativistic jet expanding in the interstellar medium, and this is this characteristic power law decay, which is dominating in the first day or two. So if we cannot see the kilonova usually during this time. In the infrared, as is shown here on this 130603b, was possible to find, thanks to the detection of this data point, thanks to HST, and then of this upper limit, what is can only be related to to a kilonova event. This is the red component, the red kilonova of this event. Cannot be a supernova, it's too quick. Cannot be a galaxy because there is this upper limit. So when we found a flattening, a shallow decay here, this is the striking characteristic feature of in any infrared of kilonova. You can see also this in the opticals, but must be so you have the blue component also in the optical, fainter than the afterglow, probably hidden by the afterglow. of the gamma ray burst, and then you have a flattening later, but it's very faint, very difficult to see. So I will use the constraints of the kilonova that we know, and we also try to show some new kilonova that was claimed in the work that we published a couple of years ago. But first, I want to show this. This is a peculiar short gamma ray burst that from last year, GB 2826. It was a redshift open 75, and is short in time. A gamma ray burst is short in time, but was followed by supernova. So we follow up this event, and we didn't find a shallow decay in the first 10 days. Here is you can see this in the red screen, but we found transient peaking much later, around 20 days. Okay, between 15 and 20 days, and this was. I will have to say this was possible also thanks to the H-band observation in adaptive optics at the Large Binocular Telescope. This was a very deep observation, 124 microns. So this is just to show that it's not possible to say that immediately when you have a short gamma ray burst, you see a shallow decay. It can be a kilonova. You have to be careful, and you can also there are a few cases where you can still find a supernova associated to some peculiar short gamma ray burst. This is very peculiar. It has other features that are more similar to long gamma ray burst, also in the gamma ray emission, and we confirm this then not coming from a merger or in this way we show that it's not coming from a merger of from a collapse, sorry, from the merger of two binary network star, but from the collapse of a massive star, so giving rise to a supernova. So how to build constraints on the luminosity? So we use the non-kilonova non up to date connected to short gamma ray burst, and we build a sample of golden sample, we call, and we found that there are events which are very similar in luminosity to 17017 or also called 2017 GFO. Here we find the ratio of luminosity between the afterglow and 2017 GFO, which is in this line here versus time. So we have a lot of events with similar luminosity. We think a factor, say 3. Then we have events which are much brighter, okay, like this one, for example, or this one here, which is very shallow. But then we found, for example, in this point, this is more than 100 times brighter. This is explained by some as to be energy injection from a magnetary into a kilonova. And then we have new events which found to have a very shallow decay. It's not easy to explain as an afterglow from a gamma ray burst. It's likely something else, like for example a kilonova. And then we have very faint events, okay, which despite the very deep follow-up do not show any shallow decay, any characteristic typical of a kilonova. So altogether, we see there is a huge, large range on kilonova luminosity for the blue component, so the optical component. In studying for the red component, okay, so there are very few events follow-up in the near infrared. We have the famous 130603b that I showed before, observed by HST, which is 3 times brighter than 17Y17. And then there are other 2 events which are also very similar to 17Y17, especially this one, 5709, and the other one which is a little bit fainter. We found the shallow decay very late in time, which is in agreement with what we knew from 17Y17. The red component is fading very quickly up to 10 days, and then we have a drop in luminosity. So altogether, we think a factor 3. All this near infrared emission is very similar to 17 GFO. So we have this big picture, a very large range of the luminosity of the blue component, the optical, okay, and component, the red component that is very similar to all the few events that we know up to now. So this is a big picture, you know. So what is different from the one I showed before here is just that I added, I liked it, the ones that are more 10 or 100 times brighter than 80 to 17 GFO, which are these events. And this
20 minutes.
Okay, thank you. And then we have new candidates that we discovered in our work we published last year. So what we can learn from this? So here I use the luminosity range that we found at the peak of the Kilonovae. This is in optical for the blue component. And you can see how this range for the peak luminosity is changing versus with the increasing redshift. Okay. So I show here with the vertical lines the binary neutron star horizon, which will have in the next LIGO and Virgo Cagra ranks, starting next year for 4 and in the future of 5. Okay, so yeah, so where the surveys, the wide field surveys can arrive, I have to say that this is very optimistic, because as we see in the last from experience, the typical surveys, small telescope can arrive to 19 magnitude here, that I put the maximum possible value, which is around 21 magnitude in Arben. So for event in 04 here, they should not have a big problem for neutron star merging events, although it's within the limit. For events that are in 05, you can see that not typical surveys, if they arrive to 2019 magnitude, will miss probably the most of the events. This is not a problem for biggest telescope like VST, which have still a very large field of view. I can go much deeper because VST is 2-meter telescope, or like the Vera Rubin telescope can go down to 23 or maybe further, depends from the strategies that will be used for targeting this to localize this electromagnetic component. What is also possible to see that it's the problem here is not the follow-up. When we found a candidate, like we did for 170817, spectroscopy on a 10-meter telescope, also imaging is not the problem. The problem is to first localize the electromagnetic counterpart. So in the future, we will have the third generation interferometers like the Einstein's telescope, the time when ELT and Nancy Roman telescope will be operating. In this case, the bulk of gravitational wave sources from binary neutron star mergers will be a redshift less than 0.5, but the localization will not improve much. They say that 50% of the event will have a localization much larger than 1,000 square degrees, and the few events with localization under the 100 square degrees will be below redshift 0.2, and to go down below 110 or 101 degree, you have to go below 0.1 in the redshift. So localization will still be a problem. In fact, if we look in the constraints, in the luminosity, the peak luminosity of the events versus redshift, in the near infrared, this is H-band, we can see that, so these lines are where of LIGO and Virgo the binary neutron star horizon for LIGO and Virgo in 05, and this is the limit for this cosmic explorer, and the bulk from Einstein telescope for binary neutron star merger will be within this around 0.5. So to go down to see this with to find this with electromagnetic follow-up will be very difficult. They are too faint for most of the surveys, and these surveys are already optimistic. This is limit for Vista, for example. It's not a problem, big problem for the brightest event, for spectroscopic follow-up for the brightest event from JWST or from ELT. It can go down, it easily go down some way to this limit. The problem is to localize this. So how to localize this? This was coming to help is the localization of the gamma ray burst, the sharp gamma ray burst associated to a gravitational wave signal, as was planned in case for Theseus proposal, which was proposed for the M5 ESA. So what we have here, the idea was to localize the gamma ray burst, the afterglow of gamma ray burst, when it's pointing our direction. So it means when we have a few events localized, okay, but they can be localized up to the higher ratios, because all the binary network star localized by observed by space GRB observatory will be also observed by the third generation interferometers. In the few cases where we are pointing our direction, we can localize the afterglow down to fewer minutes, or maybe better, and then start the follow-up with bigger telescope like 10-meter telescope or even Nancy Roman or ELT. So, to summary, what I show here that there are a lot of kilonovae, and most of the kilonovae are associated to short gamma ray burst. I didn't go in detail, but in our search for the new kilonovae, we found that only 30% of cases cannot be compared because there are only early data dominate, and other 30% are dominated by the afterglow. But for the other remaining cases, we found that two gamma ray bursts are like to faint. The kilonova was like to faint compared to AT 2017 J4. And in that case, if there was a kilonova, it was much fainter than the famous one. And in general, there is a large range of blue luminosity for in the optical. The blue component has a large luminosity. It can be brighter, 10 times brighter, or even more, even 100 times brighter than AT 2017 J4. This is in contrast of the red kilonova component, which for what we, despite there are only 3 cases observed, they are all very similar. So in the future, there we need more facilities to follow up the kilonova in the near infrared to know more also in the of this component, which is the striking particular feature of the kilonova. Despite the blue component, which is visible only for a little time, the red component is really typical of the kilonova, although it's very faint. So we need more facilities and we need to go deeper. And to go deeper, this is the WST and ELT will be very helpful because they can expand the reach of kilonova detectability up to redshift 4.5 or even more in few cases. But we need to localize them first, the electromagnetic counterpart. And they show us that localization by a gamma ray burst, in the few cases, this could be very helpful. So I finished, but first I want to show something that is not totally completely related to, it's not related to kilonova, but it's related to gamma ray burst. Last is something I'm working in these days. This is a gamma ray burst 290905A. It's a redshift of 6. And this is, we are working on this is one of the brightest gamma ray bursts and follow up by the brightest optical afterglow. One of nice feature is that they follow up simultaneous from gamma rays to optical, and these are the this data right here is the follow up by the 60 centimeter RAM telescope, and more will be published in a suite of papers on which we are working now, including one which I'm leading. And thank you.
Okay. Thanks, Andrea. Are there questions? Yes, I see one by Martin, please.
Hello, thank you very much for the very nice talk. It was interesting because speaking of James Webb, I was writing a proposal on target of opportunity for the first year to follow up gravitational waves with the accompanying with the short GRBs, and it was actually rejected. By the way, saying that there will be no like a target of opportunity for James Webb for the first year. So that's just a comment. And second, I wonder, like you mentioned the blue component, and you talked about it less than the red component for certain reason. But would it make sense? I know there are some like wide field survey telescopes planned to be launched in ultraviolet. Would it be also bright in ultraviolet, or does it peak around the U filter? Which was detected from the ground. So is there a chance that the emission would be like a little bit earlier in the ultraviolet?
Yeah, I didn't mention this because what we know from in ultraviolet from the follow-up of short gamma ray burst, and also from ET 2017 is not much. Okay, so it's expected also ultraviolet component, polar component, especially emitted in ultraviolet. This will also be particular. But it's also expected this to disappear very quickly. So in case of ET 2017, we started observing 11 hours. Okay, and I think yeah, this also where we have the first data from UVOT, which was the only one following up in ultraviolet. For the gamma ray burst, usually there is no coverage in ultraviolet, so I cannot say anything on the luminosity constraint. The only thing we know for Kilonovae now comes from ET 2017 GFO. And we started too late. Probably ultraviolet component is expected to already be the polar ultraviolet component is expected to be fed already, not visible. But this is something will be very important because some models say that this will be another additional component of the structure or what is emitted by merging of two neutron star. So we have the tidal reactor emitting the red component. We have the accretion disk with also polar component, and then we have another component, polar component emitted earlier, which should emit in the ultraviolet. And this is probably the one we should expect to see with the ultraviolet follow-up.
Does it mean, sorry, does it mean that the ultraviolet component would be visible from the also like a small angle, like opening angle of like close to the axis of the system, or would it be more spherical? Like I assume the red component is roughly almost spherical, right?
Yes. This is an interesting question. I think there was so the models. Okay, the red component is basically isotropic; it's more spherical. There is some dependence on the inclination from the blue component, which is the one closer to the merger, and the ultraviolet component. I'm not sure. I should okay, but should be also have a dependence from the inclination. What we show in our work from last year is that the blue component, at least, doesn't have a very huge dependence from the inclination. And this also was shown by other works, and this is also expected from modeling. There is before to see a huge dependence on the inclination, you have to go to very large angles. For ultraviolet component, I don't know. I should look. Okay. Yeah.
Thank you.
You're welcome.
Are there any other questions? I can take the chance to ask one, which is probably not very smart, but that's not my topic. I wanted to know about the neutron star black hole events you mentioned at the beginning. They both were located around 300 megaparsec. Is that a coincidence, or is there a strong selection bias, and this is where you're going to observe them?
This is probably a combination from the increasing volume in the universe and with decreasing sensitivity of the instruments, of the interferometers. So yeah, I think, but yeah, it's an interesting question. It's not a very, it's not a stupid question, obviously. It's
Okay.
nice, but this is probably the reason. Yeah, I didn't show. And if one look at this figure, there are not just two events. This is the third one. Okay. And this is the 1908-14, for which also we did follow up. But here, hidden, there is another one, 1904-26, which is also a candidate, not a star. And this one appears, it's also around 300 megaparsec. Is this one here, 270. So you see, what you notice is makes sense. They are probably just at the boundary of increasing volume and diminishing sensitivity.
Okay. Thanks. We have another question by Pian, please.
Yeah, I only wanted to make a comment to Martin Topinka's question about the blue component. Assessing the blue component, the collimation of the polar component is difficult. It's impossible based on the present knowledge. Both the neutron poor and the neutron-rich components may have a strong, very early UV emission. There is one team, one single group who could observe the August 2017 event immediately during the first night, not 12 hours late, 11, 12 hours later, like almost everybody else. They have a spectrum. It's Chapi and collaborators. I can send you maybe in the chat the spelling, the reference. In that paper, they show how blue the spectrum is at that very early epoch. It is significantly bluer. It's a clear black body. That the instrument they use is not very efficient in the ultraviolet, so they don't go as far in the UV as one would like, as one would hope. But they show that the spectrum peaks at significantly bluer wavelengths than the day after. Concerning observability prospects, there are two small missions approved for the future for launch in the next years, which is one is NASA, Gucci Dorado, and the other one is Israeli Space Agency mission, Ultrasat. They are both optimized to detect very rapid UV transients.
Thank you.
Thank you. Can I have one more question if there is nobody else?
Wait, sorry.
I will wait
there is Capi too. And
if I may, if I'm not off topic, I apologize. I entered only 10 minutes ago, so I missed most of your talk, Andre. I'm sorry. But it was, I mean, I saw about the future future perspectives and future missions, and I was wondering if you showed maybe already, or what you could say about X-ray wide field missions. In particular, I'm thinking about Einstein probe, which is about to fly in a few years, and which will have also ESA participation in it. And I was wondering if you expect some detections also in X-rays with wide field X-ray. missions.
Yeah, I didn't talk about this. Okay, Kilonova can also have a non-thermal component, which we start to see now for a 170817. I apologize, I didn't want to go in the direction, but this is maybe we start to see this like for Chandra and with Chandra and XMM. So we need more data to be sure. Yeah, this is something that could be maybe also observed with Einstein Pro. Though I don't know up to which redshift. I should look at the sensitivity. And also we don't know much now, which this component is not really confirmed. Then we see the afterglow, of course, short gamma burst. We see the afterglow in the X-rays, and this is we observe already with Swift XFT. We saw with Chandra, we saw with XMM, and also the case of a redshift 6 GRB. We can also, it's not short gamma burst, but up to very high redshift it's possible to follow up gamma burst afterglow in X-rays. But yeah, thank you. I didn't mention about this possibility, which was a bit, yeah, a little bit off topic from the optical and near infrared follow-up of the real Kilonova component, which is the thermal component.
Thank you.
Well,
Okay. Any last very pressing comment or question? I see both hands of people that spoke already, so I don't know if they forgot to lower the hands or they want to say something more. In case, do.
I don't know if I can because I asked already one question, but
yeah, okay.
Sorry, you mentioned the difference between let's say to distinguish supernova. Is there like a after, like many let's say I don't know, from 10 to 30 days after, and to see the red component from kilonova? Is it easy to distinguish if you see just the late? You have only the late observations.
well, a supernova. I mean, the feature of the, like in this case, this is 130603b. This is just one data point and one upper limit. Okay, in the light, nothing else. There is no spectra, there is no other bands, but this cannot be a supernova. This is point here is 10 days, and then there is nothing else. In this band, you should see this redshift of 0.3 or something. You should see this component also after 20 days, 30 days. You should see something here. You should pick with this redshift around here. You should see it, but here we have a lot deep limit. So there is no way to, I mean, even the fastest supernova cannot evolve so quick. And we should see something also in the other bands. In this case, there's this upper limit, okay, from HST. This is too red for a supernova, okay? This big, huge color difference. This is too red for a supernova.
From a previous plot, I had an impression that this is very exceptional, that usually the light curve is much shallower, but maybe I was wrong. From the other cases you've shown of the known kilonova, yeah.
Depends a lot to which bands which maybe we can talk this on email, but
okay.
Depends a lot on which bands you consider, because in the in the optical the evolution is much quicker. But even in the infrared, we have this shallow. But anyway, there is a drop expected to around a week, 10 days, and the supernova after that time should start peaking around that time. So it cannot be the two things.
I see. Okay, thank you.
Well,
Okay. thank you all for this nice discussion. I think for today it's the end. So we reconvene next Tuesday. We will have an astrophysics seminar, even if like schools are closed in Italy, etc. But we will keep having the astrophysics talk. So thanks, Andrea, and bye to everyone.
Bye. Thanks a lot.
Bye bye. Ciao, grazie.
Thank you very much.